So at equilibrium, the rates of the forward and reverse reactions are equal, not the concentrations, the rate of reaction. Well, what can we know about the concentrations? Because concentrations are important to us. Well, the equilibrium constant is a way that we can quantify, put numbers on the relative concentrations of reactants and products at equilibrium. So if we look at this generic chemical formula, A plus B is in equilibrium with C and D. So A plus B are the reactants, and they react and they form C and D. These are the products. But those products can do the reverse reaction and reform the reactants. So this is Narnia and Middle Earth, and people are moving to Middle Earth and people are moving to Narnia. And eventually, usually we think about starting out with just A and B and without any C or D. And so initially, there's a big push to go over here. That rate is high because the concentrations of A and B are relatively high. But as they react, the concentration decreases and this forward rate goes down. That causes, but the concentration of C and D have been increasing, which causes the reverse reaction to increase. But eventually it'll come to a point where they're equal. So what's this equilibrium constant? The equilibrium constant is defined as the ratio of the concentrations of products over the concentrations of reactants. And they are raised to powers corresponding to the coefficients from the equation. So the equilibrium constant, here are the products. It's always products over reactants. So the concentration, when we put brackets around something like this, we mean the concentration in moles per liter, and we'll talk more about that concentration unit in another chapter. But brackets around a chemical formula just mean the concentration. So it's the concentration of C raised to the power of its exponent. There's the coefficient, so raised to the power of its coefficient. So if this was a 2, then we'd have C squared. D raised to the D power. If this was a 3, then we'd take this concentration of D and cube it. And then we're going to divide it by the concentrations of the reactants, also raised to the powers of their coefficients. Sometimes talking about it in generic terms is more difficult than looking at a specific example. So if we have this equilibrium reaction, 2N2O5 reacts to form 4NO2 plus O2. And then these things are also reacting to reform the product, the reactant. So this is an equilibrium. That's what the double arrow means, that the reaction is going in both directions. So then the equilibrium constant for this is the concentrations of the products. So NO2 is one of the products, and then it's 4NO2, so this is NO2 raised to the 4th power. 1O2. O2 raised to the 1st power. So this was an implied 1, and this is an implied 1, because we don't need to write the 1 there because it doesn't change anything. And then it's divided by the concentration of the reactant. Here there's only one reactant. 2 of those, so this squared. The coefficients from the equation become the exponents in the equilibrium expression. And you may be wondering why. Mathematically, this is the description of what's happening. So there's very sound math behind this, but we're not going to go into it. They've studied this, and this describes the reaction. Any questions? It was kind of a leap from what we've been talking about, I know. So let's do an example. Let's write an equilibrium expression for this chemical equation. So we're going to say KEQ for equilibrium constant is equal to, so we're going to look at, it's always the products over the reactants. So here's our product, HF. So we'll put brackets around that to indicate the concentration of HF. And there's a coefficient of 2. So that means that becomes the exponent for that one. Here's one of our reactants is H2. So that's going to go on the bottom inside of brackets. The brackets meaning the concentration of H2. What's the coefficient for H? 1. So then the subscript here, the exponent is 1. Do we need to write that? No. Anything raised to the first power is just itself, so it's not necessary. And then that's going to be multiplied by what? What else we? F in brackets. F2. This is the other reactant. Reactant. The other reactant, and this one also has an implied 1 as the coefficient, and so it would have an implied 1 as the exponent. And that's the equilibrium expression. Any questions? Well, what does this equilibrium constant mean? If the equilibrium constant is big, and when we mean big, we're talking big numbers. Here, this one is 1.9 times 10 to the 19th. It's a really big number. Well, what is the equilibrium constant expression for this? KEQ equals HBr squared, right? Divided by, yeah, you guys are getting it. So if this is a really big number, what does that tell us about the relative concentrations of reactants, products and reactants? Which one must be larger? If this whole thing is a big number, that means that the concentration of the products must be large compared to the concentration of reactants, which tells us that this equation, this reaction goes more to the right. It's tipped. The concentration of products is greater at equilibrium. Greater concentration of products and lesser concentration. So that means the KEQ being large tells us that at equilibrium, the products, oh good grief, start over. If KEQ is large, that means that at equilibrium, the concentrations of the reactants are small compared to the concentrations of the products. It's just reversed, yeah. So if KEQ is small, well down here, the equilibrium expression for this one is what? NO squared divided by N2, the concentration of N2 and O2. If this number is small, this whole thing is a small number. That means that the concentration of the product must be a lot smaller than the concentrations of the reactants. That means that the reverse reaction is favored. Now we have large concentration here and small concentration of products.
We derive that from the number.
We're getting that from this number. We're looking at this 4.1 times 10 to the minus 31. That's 0.3041. That's a really tiny number. That means that at equilibrium, there's almost no product. This is really small compared to the concentrations of the reactants. When the equilibrium constant is large, like 1.9 times 10 to the 19th, It's a very big number. Then the concentration of the products must be really big compared to the concentrations of the reactants. Meaning that this reaction goes mostly towards the products. There are others where the equilibrium constant is closer to 1, and those are more of a 50-50 kind of a deal. So if we have a large equilibrium constant, these slides are referring to the previous slide. There's the equilibrium constant. If this is the expression, if this is a large number, that tells us that relatively we have a large number of product molecules compared to reactant molecules. If KEQ is a small number, here's the expression, then the numerator must be smaller than the denominator for this to be a small number. And so here we have an illustration, and we see that we've got a lot more reactant molecules and very few product molecules. So that's what KEQ tells us. So if KEQ is much less than 1, the reverse reaction is favored. The forward reaction does not proceed very far. If KEQ is approximately 1, then neither direction is favored. It's kind of more of a 50-50. There's significant amounts of reactant and product present. If KEQ is much larger than 1, then the forward reaction is favored, and the reaction goes almost to completion.